So in this session, we will be discussing about the numericals based on Nernst equation. It is very important in the point of view of your board exams. At least one problem will be from your Nernst equation. That is, you have to apply your Nernst equation and you have to calculate the E of this cell or E of the half cell. So it's a compulsory problem from your electrochemistry. The first problem is find the E, that is the electrode potential. As I have told you, IUPAC accepted. According to IUPAC, electrode potential means reduction potential. So you are calculating the reduction potential, electrode potential of Fe2 plus aqueous. So the concentration of Fe2 plus aqueous is 0.01 molar. Fe solid, it's the electrode dipped in this aqueous solution at 25 degrees Celsius. That's nothing but your 298 degrees Celsius. In your previous video, we have made a mistake of 25 degrees Celsius means 293 Kelvin. Sorry, make a correction of it. That is 298 Kelvin. So 25 degrees Celsius is nothing but 298 Kelvin. If standard electrode potential, they have given the standard electrode potential, this information is taken from your electrochemical series. So E naught of Fe2 plus Fe is it is equal to minus 0.45 volts. So now you have to calculate the E of this half cell. You can see there is only one metal, iron metal dipped in iron solution, that is Fe2 plus solution. As a result, it is a half cell. So first let us see the half cell reaction of this half cell, that is half cell reaction. The half cell reaction is Fe2 plus aqueous plus 2 electrons give rise to Fe. This is your solid. You can observe this is a reduction reaction. So it is a reduction half reaction. Reduction half reaction. It is a reduction half reaction. Fe2 plus 2 electron give rise to Fe solid. From this I can withdraw the information that N is equal to 2 electrons because we require this N. So N is equal to 2 electrons. Now let us take the Nernst equation to apply here. So Nernst equation, before taking a Nernst equation, let us take the concentration of Fe2 plus. It is equal to 0.01 molar. It is given in this half cell representation. This is the half cell representation. So concentration of Fe2 plus is 0.01 molar. Also they have given E naught of Fe2 plus divided by, that is Fe2 plus Fe is equal to minus 0.45 volts. Nernst equation going to be E is equal to E naught Fe2 plus, E naught E is equal to E naught minus 0.0591 divided by N log of concentration of product. Product is Fe, concentration of product. It is Fe divided by concentration of reactant. Reactant is your Fe2 plus. Fe2 plus. We know that concentration of iron, it is equal to 1. That is because in Nernst equation I have told you that the molar concentration of pure substance, either it is a solid, liquid or a gas, it is equal to 1. So concentration of Fe is equal to 1. Concentration of Fe2 plus is given here. E naught is also given is here. So N is also been found out as 2 electrons. So substituting it becomes E naught is minus 0.45 volts minus 0.0591 divided by 2 log of 1 over concentration of iron is, that is Fe2 plus is 0.01. So I can write this as 10 to the power of, in terms of 10 to the power I can write it as, if I shift it to 10 to the power like this, it becomes 10 to the power of minus 2. 10 to the power of minus 2. Then minus 0.45 volts minus 0.0591 divided by 2 log of, if it is going to your numerator, from denominator to numerator, 10 to the power of minus 2 becomes 10 to the power of plus 2. That is log of 10 to the power of 2. You can write this as 2 log 10. You can take it as log of a to the power of b, which is nothing but your log of B log A. So it can be taken as log of, that is 2 log 10. So this becomes minus 0.45 into, minus 0.0591 divided by n into 2 log 10. 2 log 10. Log 10 is 1, so this value becomes 2. So here n is 2. N is 2. So this will be minus 0.45 minus of 0.0591 divided by 2. 2 log 10, 2 remains as it is, log 10 is 1. So 2 into 1, it is 2. 2 gets cancelled, and the final answer would be, that is the E of Fe2 plus to Fe is equal to, this will be the E of, that is the reduction potential of Fe2 plus to Fe, that is minus 0.509 volts. So this is how you calculate the half electrode potential, that is the reduction potential of this reduction half cell. So the next question is, represent the cell. So you have to write a cell representation in which the following reaction happens, that takes place. The reaction is this one: magnesium, that is it is losing electron, which means it is oxidizing. Silver, it is gaining electrons, which means it is reducing. So this is the reaction. They have given the reaction, cell reaction. You have to represent the cell reaction. That is, you have to write the cell representation for this reaction. Also, calculates this E cell, that is your cell potential at any condition. If E naught cell is equal to 3.17 volt, that is the standard cell potential is given. You have to calculate the cell potential. Standard cell potential is given. You have to calculate the cell potential. So first let us take the first half of the question, that is represent the cell. That is, you have to write the cell representation for this reaction. So let us see what is happening. So as I have already told you, magnesium is undergoing oxidation, loss of electrons. Oxidation always takes place at anode. Lone, I think you know this, you remember this lone. Left side oxidation, anode negatively charged. So magnesium acts as anode here, because it is undergoing oxidation. Silver, it is undergoing reduction. Obviously, it has to act as your cathode. Anode is written on the left side, cathode is written on the right side. So first thing, magnesium is undergoing oxidation. So it is undergoing magnesium solid to magnesium 2 plus. You have to write the concentration, aqueous. The concentration is 0.130 molar. Oxidation is happening. You have to separate it by a single line. Next, silver, anode is completed. Left side anode is completed. Right side, it is your cathode, silver. Silver is undergoing reduction. So it is Ag plus. It is undergoing reduction to Ag. Aqueous. Write the concentration of this aqueous Ag, that is aqueous Ag, the concentration is given to be 0.0001 molar. Ag solid. So separated by a single line. Since this is a complete cell, you have two different half cells, oxidation half cell, reduction half cell. Obviously there should be a salt bridge, hence it has been separated by two lines, which means that is a salt bridge. So this is your oxidation half cell that acting as your anode. This is your reduction half cell, reduction is happening, Ag plus to Ag, reduction half cell, Mg to Mg plus oxidation. This is your reduction half cell, this is your oxidation half cell. Since there are two cells, two different half cells, you have to separate it by a salt bridge. So this is your first portion of your answer, that is represent the cell representation of this above reaction. Now we have to solve the second half of the question, that is you have to calculate the E cell using your Nernst equation. E cell using your Nernst equation. So equation becomes E cell is equal to E naught cell minus 0.0591 divided by n log of, since it is not a half cell, it is a complete cell, you have to write it as oxidized form by reduced form. That's nothing but simply product divided by reactant. So I have already derived this equation in your previous session. Directly I am going to write it as oxidized form, species or form, molar concentration of oxidized form or oxidized species divided by molar concentration of reduced form or species. This is your Nernst equation. Now, according to your equation, what is required is molar concentration of oxidized form, which is undergoing oxidation. Magnesium is undergoing oxidation. What is concentration? It is your 0.130 molar. So this is have been given in the problem itself. Reduced form, which is undergoing reduction, silver is undergoing reduction. What is concentration? It is 0.0001 molar. So your denominator is also given. The only thing you have to calculate here, it is your N. That is, what is the number of electron transferred in this reaction. Very simple. Let us see how to calculate this number of electron transferred. So let us write the two equations. In this one equation, you have two equations. One is reduction, the other one is oxidation. I will separate it out, then I will tell you how to calculate this N value. Say for example, first thing, magnesium to Mg2 plus 2 electrons, right? Magnesium to magnesium 2 plus means 2 electrons have been removed, so plus 2. The other one is 2Ag plus 2Ag. So 2Ag plus 2Ag. Reduction is happening. Ag plus means 1 electron into 2 means 2 electrons. So plus 2 electrons. 2 electrons. Reduction, this is your oxidation, this is your reduction. Oxidation, magnesium 2 plus means you have removed 2 electrons. Here you have 2 electrons. Ag plus 2Ag, Ag plus 2Ag, but there are 2 moles. Ag plus means 1 electron, 2 moles of Ag plus is there, so 2 electrons. So if I cancel it out, these two things, 2 electrons, you can cancel the electrons that is present on the left hand side and the right hand side. If I cancel it out, the equation becomes Mg plus 2Ag plus give rise to Mg2 plus 2Ag. This is your cell reaction given. Now, what is the number of electron transferred that we have cancelled is nothing but your N value, that is equal to 2 electrons. Always remember, when you write this redox reaction, the number of electrons that is being transferred can be got like this, 2 electrons, 2 electrons. So totally, the number of electron transferred in this redox reaction is 2 electrons. As a result, N is equal to 2. So we have got N, just substitute the values. E0 cell is given, it is 3.17 minus 0.0591 divided by 2. 2 is the number of electron transferred. You have got here 2 electrons. So number of electron transferred in this reaction is 2 electrons. It has been transferred from magnesium to silver. Magnesium is giving electrons, 2 electrons. Silver, 2 moles of silver is accepting those 2 electrons. As a result, the N value for this reaction is 2. So 3.17 minus 0.0591 by 2 log of molar concentration of your product. Product is this one, it is concentration is 0.130 molar. This is obviously 1, that is because pure substance, solid, liquid or gas, its value is molar concentration is 1. So molar concentration of oxidized form, this is your oxidized form, or you can take it as product. Product's concentration is 0.130 molar. So 0.130 molar divided by the molar concentration of reactant, which is the reactant magnesium and silver. Magnesium concentration is 1 because pure substance molar concentration is 1. Ag plus concentration is given, it is 0.0001 molar. Log of oxidized form, the oxidized form is magnesium, its stoichiometric coefficient is 1, so no problem, 1. I have told you in your Nernst equation, the stoichiometric coefficient should be raised to its molar concentration. So 0.130 molar raised to the power of 1, it means 1 and the same. But silver, observe, silver in this Nernst equation I have told you, the stoichiometric coefficient, if it is more than 1, the molar concentration of that species should be raised to its stoichiometric coefficient. As a result here, Ag plus having a stoichiometric coefficient 2. As a result, this molar concentration should be raised to the power of 2. Raised to the power of 2, that is 0.0001 molar raised to the power of 2, 0.130 molar raised to the power of 1. That is because the coefficient of magnesium here it is 1. So hence after substituting this thing, you have to make a square of this, divide this by this, take the log of that value, then after substituting this, the E cell will be 2.96 volt. The next problem, again it is a cell, complete cell. You can observe they have given the cell representation which shows you there are two metals, so obviously it is a complete cell. Find the E cell, that is the cell potential at any temperature. Find the E cell of this cell. This is the cell. So cell has two metals, one is chromium, the other one is iron. Chromium acts as anode, iron acts as cathode. Chromium is dipped in chromium 3 plus ions, that is your aqueous solution. Its concentration is 0.1 molar. There is a salt bridge. Iron rod is dipped in iron 2 plus Fe2 plus solution. Its concentration is 0.01 molar at 25 degrees Celsius. They have given the electrode potentials of chromium and standard electrode potentials of chromium and iron. So you can observe it is reduction potential. Chromium 3 plus to chromium, iron 2 plus to iron, which means that these values are your reduction potentials. Standard reduction potentials. So the standard reduction potential of chromium is minus 0.75 volt. Standard reduction potential of your iron is minus 0.45 volts. Now we have to calculate this E cell. So let us take the formula, Nernst equation. E cell is equal to E naught cell minus 0.0591 by N log of concentration of oxidized form divided by concentration of reduced form. Reduced form. If I look into this, E naught cell is also not given in this problem. You have to calculate it. You know the formula. N is also not given. So both the things you have to calculate it. While log of oxidized form, which is the species undergoing oxidation, you can observe the species which is undergoing oxidation is your chromium to chromium 3 plus. So it is oxidation. So this will be 0.1 molar oxidized form. Molar concentration of oxidized form is 0.1 molar. Oxidized reduced form, the molar concentration of reduced form which is undergoing reduction, iron is undergoing reduction. So its reduction is happening. So its concentration is 0.01 molar. So these two things are given, oxidized form molar concentration and reduced form molar concentration is given. But E naught cell you have to calculate it, then N you have to calculate it, followed by substituting the formula. So first let us take how to calculate this E naught cell. E naught cell is equal to E naught of cathode minus E naught of anode. You know this formula. E naught cell is equal to E naught cathode minus E naught anode, or E naught reduction minus E naught oxidation, or E naught right minus E naught left. First let us take E naught cathode. Cathode is the electrode at which reduction happens. So which is the reducing species? It is your iron. So this is your right hand side half cell. So right hand side half cell which is undergoing reduction. So iron is acting as your cathode. What is the electrode potential of iron here? It is minus 0.45 volts. Minus of anode. What is happening at anode? Oxidation is happening at anode. Which is the species undergoing oxidation? Chromium is the one which is undergoing oxidation. So chromium is the anode. So it acts as anode, oxidation is happening. And chromium electrode potential is minus 0.75 volts. So this becomes E naught cell is equal to plus 0.30 volts. This will be your E naught cell. So E naught cell is now being calculated. Here I have to substitute it. The next thing is I have to calculate this N value. So in your previous problem also I have shown you how to calculate your N value. So let us take the reaction here. This is the redox reaction happening. We will split into a reduction reaction as well as an oxidation reaction. First is your chromium. Chromium give rise to chromium 3 plus, means 3 electrons have been lost. So plus 3 electrons. 3 electrons have been lost, removed from the species. So 3 electrons. Oxidation, sorry, this is your oxidation. Now it is your reduction reaction, I have to take it. This is your oxidation. Reduction, I have to take it. So reduction is Fe2 plus give rise to Fe. So 2 electrons have been lost. To get Fe, I have to add 2 electrons. Have to add electrons. You can observe there is no equalization of electrons. Here it is 3 electrons, here it is 2 electrons. So what should I do? I have to take equation 1, equation 2. I have to make these electrons equal so that I can cancel it out. So into 2 into 3. As a result, I get this equation as 2 moles of chromium give rise to 2 moles of chromium 3 plus 6 electrons into 3 moles of iron 2 plus 3 2s are 6 electrons give rise to 3 moles of iron. Now I can cancel your equation, that is 6 number of electrons to get you 2 moles of chromium plus 3 moles of iron give rise to 2 moles of chromium 3 plus 3 moles of iron. So this is your balanced equation. That is your reaction, balanced redox reaction for this cell. Now if I observe the number of electron transfer across this redox reaction, the number of electron transfer N, it is equal to 6 here. 6. In your previous problem, we have not multiplied by any number because the left hand side number of electrons and the right hand side number of electrons were obviously balanced by 2 electrons. As a result, N was 2. Here it is not balanced. Here you have only 3 electrons, here only 2 electrons. So I have to balance it first, then calculate the number of electrons. So total number of electrons that has been transferred in this reaction from chromium to iron. Obviously it is from chromium to iron, it is equal to 6 electrons. So N is equal to 6. You have got E naught of cell, it is plus 0.34 volt. Then N, that is 6, N is equal to 6. Now I have to substitute it. The equation becomes E cell is equal to, E naught cell is plus 0.30 minus of 0.0591 divided by 6 log of molar concentration of oxidized form. So molar concentration of oxidized form is your chromium molar concentration is 0.1. So you have to observe this reaction, this is your balanced reaction. You can observe chromium has been raised to the power of 2. So which means that its stoichiometric coefficient here it is 2. So 0.1 raised to the power of 2 divided by reduced form which is undergoing reduction. Reduction is undergone by your iron. You can observe iron. Iron has been accommodated with the stoichiometric coefficient of 3 and its molar concentration is 0.01. So it's 0.01 raised to the power of 3. Here it is raised to the power of 2, here it is raised to the power of 3 because I have told you in your Nernst equation, if your chemically balanced equation has any stoichiometric coefficient other than 1, you have to raise the molar concentration in your Nernst equation to that power. As a result, this is your balanced redox reaction of the cell. This is your balanced redox reaction of the cell which has 2 as your stoichiometric coefficient of chromium. So hence 0.1 molar concentration of chromium raised to the power of 2. Iron has been accommodated with 3 as the stoichiometric coefficient. Iron concentration is 0.01 molar raised to the power of 3. This I can write it as 10 to the power of minus 1. This I can write it as 10 to the power of minus 2 whole square whole cube. If you have the complete substitution of this formula, E cell is equal to plus 0.30 minus 0.0591 divided by 6 log of This I can take it as 10 to the power of minus 1 whole square divided by, this I can take it as, if you shift the point, it becomes 10 to the power of minus 2 whole to the power of 3. So, E cell, it is equal to 0.26 volts. So, after substituting these values, taking the log of this value, so you can make it as 10 to the power of minus 2 into 3, 10 to the power of minus 6, 3 2s are 6. This 10 to the power of minus 1 into 2, 10 to the power of minus 2. Take this to numerator, it becomes 10 to the power of plus 4, 4 log 10. So 4 log 10 is 1. So 4 into this substitution, you get this value as E cell is equal to 0.26 volts. So that's the answer of this E cell. You have been calculated the E cell for this given cell of chromium and iron. A calculation here, it is 10 to the power of minus 2, 10 to the power of minus 1 whole square, it is 10 to the power of minus 2 divided by 10 to the power of minus 2 into 3, that is minus 6. This will be 10 to the power of minus 2 into 10 to the power of plus 6. That is because if it goes to numerator, it becomes plus 6. That is equal to 10 to the power of plus 4. If you take log of this one, this becomes 4 log 10. 4 log 10. Log 10 is 1. This value becomes equal to 4. So this whole value it is equal to 4. So 4, 6, just cancel it out by 2. So 2 2s are 4, 2 3s are 6. Then whole value you minus this from plus 0.30 volts. You get this value, that is E cell is equal to 0.26 volt.